All right, everyone, so today I hope will be way more interesting. Today is the intro to quantum mechanics, so you're going to see the Schrodinger equation. So I'm going to cover the Schrodinger equation today, which I don't know, I had heard of the Schrodinger equation in high school, so I was all excited about this, but you may not be at the end of class, so because the Schrodinger equation is unfortunately not like the thing that is quantum mechanics. The Schrodinger equation is not something you actually solve to do quantum mechanical stuff. The Schrodinger equation ends up being more like a referee. You think like, well, how do I score points? The Schrodinger equation tells you that. No, the Schrodinger equation is really the referee. How you score points is really an exercise of mathematical complexity that is truly mind-numbing. And you'll see why that is at towards the end of class. Okay, I did want to take just some nuts and bolts. Remember, homework's due Wednesday. It's actually relatively easy, but now that we're doing real quantum, it's going to get harder. Let's see, what else was there? So I sent you some emails. The main thing is I do feel like I just was not comfortable with what I did on Friday when we were finishing the Planck distribution. I just tried to make that average energy. It's several steps. It's that handout I sent, and as I incorporated into the video. The average energy calculation for the Planck distribution is unfortunately a couple of steps, so I tried to just gloss over that, and I just wasn't comfortable with that, so I ended up filming that later and splicing that into a video. Big picture, I'm not going to have you like on the last question on the exam be like, hey, rederive the Planck distribution, because that's absurd, and even I struggled with it, obviously, so don't look for something like that. In the big picture, the Planck distribution, remember that we start with the Planck distribution. This is fairly traditional in this class to start with Planck distribution before quantum, because Planck has a lot of quantum mechanical principles in it without being quantum mechanics. It has waves in a box. So quantum mechanics is all about waves. They have to fit in the box. Planck has waves in a box. That's why it's a good start. The Planck distribution involves a second order differential equation. That was what we did on the first day with Ampere's deal. The double derivative of x plus double derivative of y equal to the double derivative of time. That is a second order differential equation. That was in the Planck distribution. It's also in the Schrodinger equation. So you saw a lot of common elements. Now, I feel like I should start with the Planck distribution, but here's the part. I just thought of this the other day, a description, a big picture about why the Planck distribution is simultaneously kind of difficult, but in a different way than quantum. And so anyway, I wish I had thought of this the other day when we started on this, because I hopefully have a good way to take a big picture of this, because the Planck distribution, I really find it to be difficult to be blunt, but the reason is because it's several things are happening at once, and I have a hard time keeping it all together. So it's kind of like electronics. Every part of the circuit affects every other part of the circuit. I don't know how anybody designs circuits. It's very confusing to me when I've got all this timing circuit, but then I add a wire to it, then everything goes to hell, right? The whole thing has to work together simultaneously. That's just not something I'm good at. Okay, when it comes to the Planck distribution, let me summarize that with this little diagram I have, this silly diagram I have here. And what I'm trying to draw here is, did any of you ever play, it's kind of like a little kid's game. It's a little game where you get 3 posts and there's rings on them. Large rings and small rings, and you have to move it, right? You have to move them over, but you can never put a large one on top of a small one. You ever seen that before?
Never figured it out.
No, it's not that hard. But anyway, so what I've got here is a post, and I'm going to put little rings on them. Okay, the rings are photons, and I'm going to create the spectrum. Okay, now, notice that I've drawn wavelength, and I've drawn little posts. The little posts are like modes. This would be the mode like this, right? Here's the weird square-shaped light bulb. So there's the first mode. And anyway, so it's a light bulb. Okay, then this one would be this mode, and this one would be this one. Okay, so anyway, that's what those posts are. Not too bad, right? We started with that. Hopefully that did not blow your head off. Notice that I actually draw them closer and closer as I go to higher wavelengths. So anyway, that's just a little subtlety. Let's see, what else do I want to say? Longer wavelengths. Okay, notice I have different heights. Different heights are that degeneracy factor. That's where, remember when we were talking about how we have a wavelength associated with one node and 0 nodes, and there's actually 2 ways to do that. And so we have this degeneracy factor that ends up affecting the Planck distribution and the total energy of the light bulb. That's in the height of the post. That's what I'm trying to do there. Now, it turns out that back in 1900, when people were trying to figure out light bulbs, they had light bulbs, and they started trying to figure them out, Rayleigh Jeans before Planck was these two people, and they came up, they actually had this part right. They knew that there were modes, and they had the degeneracy factor right, but they made a mistake because they thought photons are particles, and they are. I mean, so that isn't wrong, but their energy is 1/2 kBt times 2. That's the degree of freedom, kBt. Okay, so what's happening is 1/2 kBt. What is that? What theorem? Equipartition theorem, and 2 is the degrees of freedom. So they thought that photons had kBt degrees of freedom, and here's where they really, and that's wrong, right? We know that reality that the energy, I have to spell it out because you know E is electric field at this point, is hc over lambda, right? So that's what they screwed up. And even that's not right. Remember that you can have more than one photon, so that's really the energy. Okay, so they thought that these were particles, and the other screw up was they thought that if a photon can exist, it does exist. So they thought that the spectrum from a light bulb, according to them, would look like this. It would scale the spectrum, so according to these guys, the spectrum is basically proportional 1 over lambda to the 3rd power, which looks like this. I'm not drawing it super well, but okay. Now, what do you think the energy output of that is? I gave a hint there when I graphed it. Infinite, right. Their big mistake is, okay, the calculation of energy, not right, but not a big deal. Where they screwed up was saying that if a photon could exist, it does exist. And no, we all know that the reality is that Planck got the energy right, and he added the Boltzmann factor. Now this is where I was saying that I want to add little rings to this. So Boltzmann factor adds a certain number of rings, but what it does is when you get to higher and higher energy, it actually goes back down. The Boltzmann factor kills it. And then no more. So the Planck distribution actually looks like this. So that's how, and that's reality. When we look at the spectrum of the sun or a light bulb, we get the Planck distribution. Again, I'm not drawing that very well. So again, I hope this just kind of summarizing. I just want to point out that I didn't really think any of this was particularly hard by itself. It's just that we have 3 things. One was what I would call the mode structure. Those are the lights that, what wavelengths fit in the box. Then you have, let me use some more advanced language, density of states. That's the height of the post. That's the degeneracy thing that I just got rid of. And then you got the Boltzmann factor as well, which just says that you can't have energy, you can't have X-rays coming out of a light bulb because it's too high energy, and I explained that last Friday. And then you get all three of those and you integrate them to the result, okay? Which is that the energy of a light bulb is proportional to KT to the fourth power. It's some constants, whatever. I'm never worried about constants, but that's the part that matters. It's KT to the fourth power, and that's the energy out of a light bulb. Okay, very okay. Again, I wish I had thought of this, maybe making, if I did that in Illustrator, I could do way better, obviously, but I wish I had thought of that maybe before I had even started on this. I just thought of this morning. So, any questions before we go on? We're okay. So, alrighty. Now the test is in 2 weeks, by the way. So you know this Friday, all new people. What we do is, students generally, every class I've ever taught want to do the review session on Wednesday before the test. Because for one, that's probably when you've started to study, which angers me. But I can't control you. Wish I could, but I can't control you. Also, what I do agree with is you don't want me lecturing, you don't want me to do a review session on Friday, then have 2 lectures and then the exam. No, that actually is a bad idea. So what we typically do on Friday is double lecture Friday and then I'll review on Wednesday. Obviously, the extra Friday would be a great review day, but for the reasons I just said, that doesn't work out. And also, the exams are on Friday, and that gives you both hours. So anyway, so that's coming up, and so I'll start on the test soon, and I'll start hemorrhaging hints for what's on the test. I'm going to design the test to be identical for what you saw last semester. Short answer, easy questions, hard questions, exactly like last semester. And so when it comes to Planck distribution, look for describing words, especially like what I just did there. That would be a very good, just tell me what the Planck distribution is. There you go, that's a question. I would probably make it a little easier than what I just said, but anyway. All right, so moving on. Wherever we're at in the textbook, I'm not even sure. I have the pages delineated in the website. And Schrodinger equation. Okay, so this is really quantum mechanics, And I did mention that I hope that I kind of borrowed a little bit of lecture time last Friday on the extra hour. Sorry about that, but I couldn't help myself. 1930s, early 1930s, what's going on is people are realizing Einstein has come out with that equation for relativity. And a natural output of that is light has momentum. Light should not have momentum because it has no mass. They know light has no mass, but momentum being mass times velocity means light has no momentum. Einstein has this incredibly different equation for energy. Energy is not 1/2 mv squared, it's that rather slightly more complicated thing. And a consequence of that is light can have no mass but still have momentum, and that's why it can knock electrons out of semiconductors and what was, the photoelectric effect. So, what? Okay, I also mentioned heat capacity, where you look at the vibrations of atoms in that same semiconductor as moving like a wave. And that's kind of sensible. I showed you a little bit about what the lowest frequency wave is and what the highest frequency wave is, and you get good results. That makes sense. But the point is that everyone is starting to think of matter as having wave-like properties. Heisenberg actually formulates quantum mechanics, but no one understood him. I feel like him. He feels like me. Anyway, so Schrodinger comes along, and he's skiing on vacation, and it just hits him how to do this. The Schrodinger equation popped in his head. And I'll explain where he got it to. That's that kind of a more interesting story. He actually hit a tree and survived. Sometimes if you hit a tree skiing, that can kill you. We're all glad he survived because this is where we get nuclear weapons. Actually, I guess Einstein gave us nuclear weapons. This is actually, the Schrodinger equation is actually very good for understanding semiconductors. So we wouldn't have computers without Schrodinger. So I guess he was worth it. He also had 2 wives. He was supposedly a very handsome man if we were back in the 30s. He had 2 wives, and that's why he's not more famous. I mean, he is fairly famous, but no university would accept him because he had 2 wives, and that was pretty weird for them. Well, that's still weird now. So he's a pretty unconventional guy. what he came up with was, let's tell you what, let's make this real easy. Let's think about energy as being composed of kinetic plus potential energy. And Schrodinger is looking at this and trying to insert waves. So again, matter has waves. How do you get waves into this? Now hopefully we all accept this. And let me use some, let me start down the math road here. P squared over 2m plus v. And now I'm going to use the letter E for energy instead of electric field. Okay, now P squared over 2m, is that kinetic energy? Huh?
Yes.
Yeah, right, it's 1/2 mv squared. P is mv, so m squared v squared over 2m is 1/2 mv squared. So that's kinetic energy. You also did a unit analysis on your homework, and you found that this is kilograms meters squared per second squared. So that's, I know you would prefer 1/2 mv squared, but it doesn't work well with quantum mechanics. P squared over 2m is the same thing. It's a little bit more quantum mechanical friendly, so that's why we stick with P squared over 2m. You're going to see that forever, forever being the next 3 months. You're going to be seeing this every freaking equation I write, by the way. Okay, now again, what Schrodinger is looking at this and trying to figure out how to stick waves. What about waves? Remember that deBroglie said, well, let me start with Einstein says the momentum of light is just h over the wavelength, and deBroglie says, okay, well, the wavelength of matter is this. There we go. Is that. Schrodinger again thinking like, well, how do I get wavelength into here, right? And it's got to be consistent with the deBroglie. So let me again state that this is where Schrodinger is trying to come, this is definitely the energy, and he's going to insert wavelength, and I said that a zillion times, but he's going to do it such that the deBroglie formula here is satisfied. That's what he's trying to do. Okay, now last bit before we figure out how to do this for real is how can you have a wavelength without a wave? Can anyone think of something? And the hint is, by the way, I can't. Right? If you can think of something, tell me, because you probably could win a Nobel Prize. Schrodinger figures out that if he's going to have wavelength in this equation, he better have waves in there somewhere. So, like I was talking about the other day as well, when it came to light bulbs, again, this is a good reason why we start with the Planck distribution. Let's just start writing down equations of waves. And I like cosine. For doing this particular problem. It's a little bit better than a sine function for various reasons. Okay, so we're going to have a cosine, and I know that a cosine, I can describe anything that has a wavelength with this formula. So this is a wave. If you tell me I have an object, it's a wave, or it's a particle that has wave-like properties, or it's a cat, or it's anything that's a freaking wave, the one thing about the wave I need to know to characterize it is its wavelength. And if you tell me that, that's really all I would need to know. I don't even care what it is. If it's a wave-like thing, I just need to know the wavelength, and thank you, we're done. Okay, and I know, you see, when the thing, a particle, a photon, my cat, goes from 0 to lambda, cosine goes from 0 to 2 pi, right? You see, this is a very middle school level engineered description that's perfect, because when this thing, whatever it is, goes from 0 to a wavelength, cosine goes from 0 to 2 pi, which is pretty much exactly what it should do. Okay, now I'm going to simplify this, because otherwise it kind of turns nightmarish, where I'm going to, some reason my spelling is bad today, k is 2 pi over lambda, and this is called a wave vector. Who remembers when you saw wave vector before? I did show you wave vector, it was a while ago. This the beginning of Planck distributions. When I was drawing the direction that light traveled in, I called it K, I called it a wave vector. Right, so this, right, you remember that? You remember that now? Right, so this is equal to a wave vector, which is really the momentum. A wave vector really represents the momentum. And we even know, so again, whatever it is I'm describing, a wave, a photon or an electron, which has wave-like properties, or my cat, which also has wave-like properties according to Schrodinger, this is the momentum as it's traveling. So there you go. All right, next bit. So, Schrodinger, energy, this adds up, literally adds up. Got to get deBroglie shoved in there. Got to have cosines, and what's great about cosines is there's my wavelength. So what I got to do is somehow make this thing work with cosine and get that wavelength out. That's the big picture here. And what I also want to do is point out what he wants to do. What he wants to do is it's got to be in here. It's got to be in momentum. This momentum has got to get wavelength in it. He's got to be able to find wavelength inside that momentum. Now you may think, what if he was just to simply replace p squared? You know, here's another way of thinking about this. What if this is just 1/2 mv squared plus potential energy, which we could have like an electron by itself. We could have a car moving down a flat road. We can have systems with no potential energy. Let's just say we had 1/2 mv squared is equal to energy. Let's just table that. We're working with a system with no potential energy. That's not hard or weird. In fact, that's what we're going to be doing for the next month, because it's complicated anyway. If you just have 1/2 mv squared is equal to energy, and you're starting to think like, well, how do I describe that? Well, I have a function that describes the position of the electron, the cat, the photon, and 1/2 mv squared is its energy. What you're doing is what's called, when we're being fancy pants in academia, we call that classical. You're doing classical mechanics. That means Newtonian mechanics. That means it's just moving, right? 1/2 mv squared. But that's not special. There's no wavelength. Okay, what do you think instead if Schrodinger just put h over lambda? What if he just put h squared over lambda squared? What if he just inserted that? Does that do anything?
Doesn't change it.
Yeah. What do you do with that? Right. So, well, you can insert the wavelength. Well, how do you know what the wavelength is, right? So just like if you have 1/2 mv squared equals energy, you're still just writing down stuff that everyone knows. Putting in h squared over lambda squared, still it's like, well, what? What do you do with that? There's nothing to do with it. That's just weird. Okay, so here's a hint on how he figured out the next step. There's actually two ways he figured it out. I'll show you the mathematical way, but then people figure, he actually didn't tell too many people what he was really thinking, but it's actually people were able to reverse engineer his thoughts. Let me point out, this is a very simple thing. So let's put in h squared over lambda squared. So what I want to point out to you is, what I'm doing here is I'm trying to show you how Schrodinger figured out how to get deBroglie's wavelength in here. Okay, so, all right, so p squared is h squared over lambda squared. Now, just like I said, I also said, well, what the heck do you do with that? Well, hold on 1 second. Let's see here. What I'm going to do is I'm going to take h squared, and I'm going to divide that by 2 pi squared for a weird reason, because then I'm going to multiply by 2 pi squared, divide that by lambda squared. Now, what do you see here? Lambda squared, 2 pi over lambda?
The wave vector?
Okay, right. Now, also, you probably have heard of this. H bar. You've heard of H bar, right? H bar is Planck's constant over 2 pi. Anyway, I just defined that there. So this is 1 over 2m. H bar squared k squared. Okay. Okay, so p squared over 2m, when applied to a wave, better spit out h bar squared k squared. So again, it bears emphasis again. The kinetic energy part better spit out h bar squared k squared. That's its role. And it has to do it on this. It has to do it on that. How do you get a k out of a cosine? Yeah? Someone left sharp? How can I get a k to pop out of this function?
Derivative.
Derivative. Okay, now how do I do it twice?
Second
Right,
derivative.
second derivative. Right, second derivative. Okay. So let's take 1 over 2m. Let's do a double derivative. Did I put the 2 in the wrong spot? No, I did. Okay. Cosine k. Okay, now hold on a second. All right, so I got a problem. What's the double derivative of cosine?
Negative cosine.
Negative cosine. Okay, so now remember he's making this up, so he's just going to put a minus sign there. Okay, cool. That took care of the minus sign. He gets a k squared out, cool. But where's the h bar squared? It's not there, so what does he do?
Put it in.
Just put it in. He just put it in. He just put it in. Okay, so he knew this. He knew that p squared over 2m is h bar squared k squared over 2m. He knew that he could do a double derivative, but he's missing an h bar. He has a minus problem, so he just says the double derivative times minus h bar squared over 2m is kinetic energy. Okay, so anyway, I did this as a little plot device. Let's just get rid of it. Okay. This, let's just, okay, plus potential energy is equal to kinetic energy plus potential energy is equal to energy. And this is the Schrodinger equation. Seriously, this is it. We're done. You can go home now. Just kidding, you can't go home. So, yeah, that's really, now of course you can imagine it gets a little bit more complicated if we have multiple dimensions, and we're going to get there in like 2 weeks. When you start adding potential energy, let me give you an example. Potential energy, let's say we're doing quantum mechanics of vibration. That would be 1/2 kx squared, Hooke's law. Is that Hooke's law?
Yeah.
No, wait, no. Hooke's law is that
Compression of the spring.
compression of a spring is just kx. The force, but then you take the double, then you integrate it, the potential energy. Anyway, so right, so potential energy can be things like 1/2 kx squared for springs, and that will make this a bit more complicated. But regardless, we can describe a lot of things with no potential energy. It'd just be like an electron by itself, which we're going to spend a lot of time on, by the way. But now tell me, does this look that bad?
Not yet.
No, not yet. That's a much better answer. Okay, what question?
He just made this up. Like, this is not how science works, right?
Oh, okay. So now, yeah, he did just make this up. But now let me point out another little factoid, and I think you'll find this super interesting. This is the equation that describes musical instruments. No fooling you. This equation describes strings, vibrating strings. Right? It actually gets this right. For a length L, kind of like I was just doing with Planck, this is the equation that gives you standing waves, right? And you all know that musical instruments are designed to get the stringed instruments obviously, are designed to generate standing waves. And of course the craftsman's job is to tune the instrument to give you melodious waves. That's the whole point. So you have a little insight. See, this is the part that was a little bit reverse engineered from his thinking. He was literally thinking about musical instruments. Question?
But then why did you take away the cosine? What, you just erased it?
Okay. Now I said that this did not look so complicated, and right now it doesn't, but what about the cosine? right? Yeah?
Because when you plug 0 into cosine, don't you get 1?
Wait, here. Let me just apply it, Okay, so where's the cosine, right? So if I have it here, this is a differential equation. Here's how this works. Cosine kx, I believe potential energy. And then I still need a cosine. Okay, there you go. That's a little bit more accurate. Let me make this a little bit more generic. By calling, let me introduce some symbology here. Wave function. Okay, we'll call this a wave function. And here is a more standardized representation of the Schrodinger equation. It's a little, if I know what I'm writing, I can actually write it a little bit neater, which is helpful. Okay, and this is still one dimension. We will be going to multi-dimensions, including spherical dimensions, but that's about a month from now. This is hard enough on its own. Okay, there you go. See, the trick is that to add, if you have the cosine here, you have to have it other places as well. Question?
So does the wave function just denote like a general way you're going to define a wave? So could that actually vary, but it's just like a placeholder?
Yeah, right. Now, so it's like, well, the wave function, what's that part from? Okay, so it turns out, tell you what, let me hold off on that. Let me point out the hard part first, mathematically the hard part, then I'll tell you more about where you get wave functions. The hard part is, all right, look at this, right? So this is the double derivative. And now energy is like 1 joule. Let's call it 1 joule, right? And let's say that there's no potential energy. We're talking about a particle in free space. We can do that. Okay. Now you see where this can turn into a Bismarcker? Double derivative of the function has to return a joule times the function. Uh-oh. That's called a second order differential equation. Do you want to know what mathematically is some of the hardest things you could ever possibly solve? A second order differential equation. When you take the double derivative of a function, yet the function still returns. It comes back and boomerangs back in the exact same form it was in. How many things can you think of can you do the double derivative of and they haven't changed? Cosine sine. Can you think of one other thing? And I've had you do
exponential.
E to the minus ix. E to the x, e to the minus ix, right? Exponential sines and cosines. Right. Okay, but now your question is, but wave functions, well, what? Okay. As I've drawn it up here, cosine, sines, and e to the ix's are solutions. Okay, but for what? They are solutions for things with no potential energy. That would include an electron in free space, a neutron in free space. Okay, what about the cat? If you're going to have anything with some complication to it, the description of what is this the wave function for comes from the potential energy, which itself is probably a function of the letter x. Okay, now imagine this. Imagine that potential energy, let's do vibration. It's 1/2 kx squared. All right, so you see what you have to do. Now you got to get a wave function. Take the double derivative. It actually has to kill that off and still come back, but multiply by a number. Does that sound a little bit like, I wonder how you do that? Yes, it's actually horribly difficult. For the derivation of this for a vibration, again, if there's a 1/2 kx squared, it's about a 5-page derivation. You can actually Google it. If this is, okay, give you another example. What if that's 1 over r, minus 1 over r? Or better yet, don't write this down, I'm just kind of throwing some things at you. I'm just trying to see if you recognize this. What does that look like? Whose law is that? Coulomb's law. Coulomb's law. So what if, so that's a hydrogen atom, right? If I throw that in, it's a hydrogen atom. Electron and proton. That's the potential energy. So I put that, all of a sudden I'm describing a hydrogen atom. It will take us 2 full weeks to solve this for the hydrogen atom. If you throw this SOB into here, it will take you 2 weeks to solve it. And it will literally take you 2 weeks to solve it because we're going to do it, and the only way you're going to avoid it is to die. So there you go. This is where the flavor comes in. And again, the difficulty is that the double derivative of the thing has to come back. It has to come back to life. And while we're doing things with no potential energy, it's not that bad. Trust me, we're going to spend 2 weeks on doing things with no potential energy, because when I start adding potential energy, it really does truly get, I'm not ever supposed to use the word hard, but it's really freaking hard. Often it turns out, though, just like last semester, I think I told you this, it turns out that mathematicians around the 1700s, when they figured out differential equations and all that stuff, they just started solving equations just for the hell of it, and they literally solved every type of differential equation you could ever run into. Flash forward 200 years, and we discover 300 years, and we discover quantum mechanics. It turns out that a lot of the problems we were solving had already been solved 300 years before. So they had to literally go through like ancient libraries and Oxford and all that and find them. But anyway, so the solutions are out there. Okay, well that's about that. I do want to show you one or two more things about wave functions themselves. Any questions? Any questions right at this point? Question.
How does that equation tell you if the cat's dead or alive?
Okay. Tell you what. Let me let me talk about that then, and then I'll do what I was about to do. Let me give a better description, a better question of what you just actually asked, which is how do you interpret a wave function, right? So by the way, the cat is alive or dead. That's Schrodinger's cat. Maybe some of you haven't heard of this. When all of this came out, a lot of the interpretation of what I just wrote got, I have to use this word, I think this is the right word, bastardized. That means that it was sort of true, and the semi-truths got augmented to the point where they were just fantastical, right? Just wrong. I think that's the right word for bastardization. So one of the examples was, quantum mechanics says that if you put a cat in a box and you can't observe it, and there's poison in there, if you open the box up, the poison is activated and the cat's dead. If you wait long enough, obviously the cat is dead. So therefore, the cat is alive and dead. Quantum mechanics stipulates the cat is alive and dead. And the answer is no, it does not do that for the reasons I'm about to describe. What is a wave function? Okay, let's say that this is a wave function. Why not? Okay. It turns out that the interpretation of a wave function is that it is sort of a probability distribution. Sort of a probability distribution. That was the idea. Are you familiar with probability distributions?
Yes.
Yes. It's a Maxwell-Boltzmann distribution. Wave functions are Maxwell-Boltzmann distributions. But of what? Actually, here, let me make a little bit more complicated wave function. So this is the wave function on the y-axis. I just want to make it a little curvier so it's more wave-like. Okay, so what would it be? What would it possibly tell you? What do you think this wave function could be trying to tell you?
Probability or something?
Right, probability, but of what? Of having an energy, or having a momentum, or being at a certain place? It's one of those three. What do you think it's telling you?
Of the most likely energy, most probable.
It can be put into the Schrodinger equation and give you the exact energy. But that is not how it's a probability distribution. That aspect allows you to construct it. But again, here is the wave function as a function of position. So what do you think it's telling you about this particle? Where, in terms of probability?
You can
Spin?
Huh?
Spin? Like
No, that's, we're talking about that in a month.
location?
Okay, there's only one variable here.
So it's location.
Location. It actually is a probability distribution of location. Now, there's a slight problem that it can be negative, right? Cosine can be negative. So, this is called the Born, Max Born. What an awesome name. Max Born interpreted a wave function, not the wave function, but the wave function squared as a probability distribution. There you go. So you have to do stuff like this. It can't be negative. Probability distributions cannot be negative. That's nonsense. You cannot have negative probabilities. So what a wave function is a probability distribution squared. There you go. Okay. And that is not sort of a probability distribution. It is. Okay, according to the Born distribution, if you square it, it's the probability distribution. Okay, now I told you I would tell you about Schrodinger's a cat. Okay, it's 1932, and I'm a reporter, and I've seen this. And now let me bastardize it. I just love saying that word. What this wave function says is that the particle is everywhere and nowhere at the same time. Oh my God, that's so crazy. Does it really say that?
No.
Does the Maxwell-Boltzmann say that a velocity is simultaneously zero and infinite? Does it say that? No. What does it say about zero and infinite velocity? It just gives it a certain probability. Right, it's a certain probability. All the gas molecules have a certain probability of moving a certain speed, including zero, including infinitely fast. Those are zero. But anyway, just because something has a certain probability doesn't mean that it is. So the wave function here, in terms of position, when I integrate it, simply tells me the probability that I find it here, wherever there is. It's kind of, here's the cool parts, right? It says that there's actually a very low probability of this particle, whatever this is, being found here. A little bit more probability of being here, but not much more, wherever this is. So this is point 1, 2, point 3. So there you go. The wave function of the cat in the poison box is composed of a wave function that the cat is alive and plus the cat is dead. That is the wave function of a cat in the poison box. So people said, "Oh my God, it's a zombie cat. It's alive and dead." The answer is no. The answer is that there's a certain probability that the cat is alive, a certain probability that the cat is dead, but not that it is alive and dead. And so that's where things got really screwed up in terms of quantum mechanics, in terms of what we'd say layman's interpretation of quantum mechanics. It's a probability distribution. It's not an is, it's a probability. Okay, so that's how you want to interpret wave functions. Last bit, what can they do for you? Okay, now this is where, as I told you, I have never been very enthusiastic. I don't like quantum mechanics, and here's why. How do I solve this for the wave function? How would I go about that? Anyone? It's a second order differential equation. Tell you what, let me answer that in the interest of time. I'll actually show you a couple of examples on how to solve differential equations in the extra hour. We don't have an extra hour, do we? Anyway, okay, that was a throwaway lecture anyway.
Like a Laplace transform or something?
Right, so there are mathematical ways to solve second order differential equations. It turns out that this one is not, this you can do this in like 5 or 6 steps. It turns out this one is not terrible, but when you start adding like potential energy, it turns out that mathematicians sometimes have no way of like doing a step-by-step. They simply stare at the thing until they figure it out. And that's seriously, when you get to the higher level of mathematics, that's how they do it. there is no way to directly solve these. You just kind of figure it out because you're a genius. Seriously, that's how this works. So when it comes to wave functions and quantum mechanics, here's another, let me point out why this is, again, unsatisfying. One equation, two unknowns. You notice that? I don't know the wave function, nor do I know the energy. How do you solve it? Right? So if you're trying to if you want to do a brute force attack on this, you would solve the wave function, but what's the energy, right? See, you kind of have a giant problem. Quantum mechanics seems to be correct, but there is no good way to go about solving it. And that's why I really don't like this stuff, because that sucks. Okay, it turns out that the way you often do this is you just figure out the answer, you figure out the wave function. You just figure it out by other means. Now, in the case of no potential energy of an electron in a universe all by itself, that would be sine, cosine, or e to the ikx, or e to the minus ikx. Or actually, any sum of those also works. Okay, so I know that the wave function is either a sine or a cosine. I'll explain how I would, okay, so you can think of three possibilities: sine, cosine, or e to the ix, or e to the minus, instead of 4 anyway. I'll show you how to decide between those possibilities. But let's say that this electron in outer space is a cosine. There are ways to know that, and I'll show you that next lecture. But now, what do you get out of this? Okay, let's plug it in. Let's see what happens. Okay, if I do the double derivative, I'm going to end up with k squared kx. Okay, you see that? Okay, and therefore, E is equal to h squared k squared over 2m, and therefore, sorry, I'm using the word bad, k is the square root of 2me over h bar squared. Therefore, the wave function is actually cosine square root of 2me over h bar squared times x. Sorry, I'll get this out of the way. Okay, so this is the kind of thing that you can figure out with quantum mechanics. It's actually kind of similar to what we were doing with Planck, right? So what do I get from this? Okay, another thing about quantum mechanics is you have to have a lot of information about what it is you're applying the question to. You can't just come to me and say, hey, let's solve quantum mechanics. My next question is, for what? For an electron? For a cat? You have to have enough information to build a model. Now in this case, because there's no potential energy, this is an electron in a universe by itself. Because there's no potential energy. I can't think of anything else for which that's true. The other thing you have to tell me is the energy. You have to give it to me. Once you have that information, then I can tell you this. And I can tell you the wave function. And notice I can also tell you the momentum. It's h bar k. Anyway, and I'll show you how to do that next time. So anyway, where was I going? I totally forgot. So anyway, here's your brute force introduction to quantum mechanics. Schrodinger equation, wave functions are wave function squares are probability distributions. And the thing that is very difficult and painful and unsatisfying about quantum mechanics is that despite the fact that you have a Schrodinger equation, you never use the Schrodinger equation to solve it. Once you figure out the wave function by other means, you can use the Schrodinger equation to, one, check your answer, and two, learn other information. But it's not, you don't actually use the Schrodinger equation to solve the Schrodinger equation. And that is so weird, but that's how it works. All right? Okay, everyone, so